So now I'm going to go over a few problems so you can see how a one-sample t-test is implemented. Here, an insurance company is interested in knowing the average weight of cars, and that's really just for safety purposes to estimate, sort of the damages done in a car accident. And they believe that it's 3,000 pounds. So we can test this claim by going out and sampling cars, and they check 91 cars, they weigh those cars, and they find that the average weight, the typical car, is 2,855 pounds. Now, some cars weigh more and some weigh less. The standard deviation captures that variation at 531.5 pounds. So using those two pieces of information, we can run the one-sample t-test, and we're going to assume a significance level of 0.05. That's going to be our sort of level of evidence, and we want a p-value that's smaller than that in order to have a strong amount of evidence. The first thing that we want to do is set up the null and alternative hypothesis. What we're testing for is whether or not the average weight of cars is 3,000 pounds. So we're going to assume that to be true, and then we're going to try to find evidence against that assumption of 3,000 pounds. Now you can see that our sample is in fact less than that, but this may just be due to sampling variation, that if you're drawing samples from a population, some are going to be greater and some are going to be less than the true average. And so this might just be due to sampling variation. We can test that idea by using the t-test. The next step then is to calculate a t-score using your sample. We want to see how unusual our sample is if the null hypothesis is true. So we're going to put our sample first, and then we're going to subtract off our hypothesized value for where we think that true average is. We're again assuming a true average of 3,000 pounds, and then we're going to try to find evidence against that assumption. So this is just the difference between your sample and your hypothesized value. We then divide by a standard error, and this is the standard error for your sample averages. That is, if you were to repeatedly sample. It's going to be based off your sample standard deviation and also your sample size. And again, we're square rooting your sample size here in order to get things in the correct units. Once we have that, we can calculate out the t-score is negative 2.602. And it should be negative because just like the z-scores, it's centered around 0, and anything that's below average is going to be negative, anything above average is going to be positive. So here our sample is below the assumed average, and that's why we have a negative z-score. The next step then is to calculate a p-value from this t-score. The p-value is generated using the alternative hypothesis. So because we have a negative t-score, we want to reach down below this t-score to get that lower tail, and then we're going to times by 2 to get an upper tail so that we have our two-tailed test. You can do this either using your TI calculator or Excel. With your TI calculator, you're going to want to use the tcdf function. Again, I'll put a document in ReggieNet so you can see how you access this tcdf formula. And then the three numbers that you enter are the lower bound, the upper bound, and the degrees of freedom. Here, the degrees of freedom, again, it's just n minus 1. Our n was 91, so you can see the degrees of freedom is just 90. Our upper bound is the t-score we just calculated, and our lower bound is the lowest possible number that your calculator can hold. This is essentially negative infinity to the calculator, so this is as approximately close as we can get. This term, then, the tcdf, is just the lower tail. Since we're looking at a two-tailed test based on the alternative hypothesis, we're going to have to times this by 2 to make sure we're calculating the correct p-value. for a two-tailed test, and that's just 0.0108. In Excel, again, the formula you would enter is this equal sign, t-dist, and then the three numbers you enter are the t-score that you're evaluating, the degrees of freedom, and then the 1 makes sure that you're evaluating the cumulative distribution function. So you'll always put a 1 in this third term here. This formula gives you everything that's below the t-score that you enter. And again, we want to get two tails, so you're going to times this by 2, and you will get the exact same p-value. So either of these methods are going to be very, very, very close. They're essentially calculating the same formula. Based on this p-value, then, we can determine whether or not we should reject or fail to reject that null hypothesis. You can see that this p-value is much smaller than the alpha, or the significance level, that we required. And so because our data is suggesting that the null hypothesis cannot be true, we're going to reject that null hypothesis and state that we have evidence, our sample is the evidence, that the true average is different from 3,000 pounds. Now, we're not saying what we think the true average is, but we have evidence that it's definitely not 3,000 pounds. The second problem we're going to look at is rats in a maze. So here a psychologist is using statistics to make sure that the length of a maze is appropriate for their study. So mazes are classified according to difficulty, and they're measured by the average length of time it takes rats to find the food at the end. This researcher needs the maze to take an average of 1 minute to solve, so he runs a bunch of tests with several different rats, and these are the times they completed it in. So what we need to do is we need to test to make sure that the average is a minute. If it's less than a minute, it doesn't meet the required difficulty that the researcher needs. So now that you may have noticed this before in my stat lab, whenever there's data available to you, if you click this icon here, it will pop out the data and save it in an Excel file. You can copy and paste it then to an Excel file. Here I've just entered the data. But once you have it in an Excel file, you can easily calculate the average and the standard deviation using the formulas that I showed you before. So here you just hit equals average and then highlight the data. And then for the standard deviation, you do the same thing. It's equals STDEV to get the standard deviation. This is again the sample average and the sample standard deviation, and that's what we're going to use to solve this problem. So here I've written down what I just found in Excel. The sample average is 52.81 and the sample standard deviation is 14.33. The next step then is to set up our null and alternative hypothesis. We want to test the hypothesis that the mean completion for the time of the maze is 60 seconds. We're going to assume that to be true, and then we're going to see if, in fact, the true average is less than 60 seconds. Now, if it's less than 60 seconds, it doesn't meet the difficulty requirement. You can see that our sample average is, in fact, less than that assumed hypothesized value. But it may just be because there's samples vary. This may just be because we got one of the samples that happened to be less than the hypothesized value. If we were to sample another 18 rats, then perhaps we would get a value that's greater than 60 seconds. So we're going to use this sample to test that hypothesis that the true average is 60 seconds. So the next thing we need is also the sample size. So I went back and I counted how many rats we had run through the maze, and it was 18. So we're going to use that value and our sample to calculate our t-score. So our t-score again is how unusual our data, our sample is, if the true average is 60. So we're going to put our sample average first and our hypothesized value second, and then we're going to divide by the standard error of the sample averages. So we're going to use our sample standard deviation, that goes on top, and then we divide by the square root of the number of observations. You can see here that we're not square rooting this whole term, we're just square rooting the number of observations, which is slightly different than what you're used to. What you're used to is the whole term being square rooted and then PQ divided by the number of observations. The reason why we don't have to square root the whole bottom term is because our standard deviation is already been square rooted when we calculated the sample standard deviation. So we don't need to square root this again. We only need to square root the sample size to put that in the right units. And that gives us a t-score of negative 2.127. So now that we have our t-score, we can calculate a p-value, and the p-value is based off of how we've specified that alternative hypothesis. Here we're looking at less than, and so we want to determine the probability that we would see the sample average that we do, or something less than it, than the sample average that we actually observe. This is equivalent to saying that we see the t-score that we do or something less than that. That is the probability that we're calculating. We could do this using our TI calculator, using that tcdf function. Since we're reaching down to the lower tail, we're reaching to negative infinity. The upper bound is the t-score that we calculated, and then the last term is the degrees of freedom, so n minus 1, which is 17. This is going to give us a p-value of 0.0242. Similarly, we could use Excel and input the formula equals t-dist. Our t-score goes first. This formula gives us everything in the lower tail, so everything below this value, and that's what we're looking for because the alternative hypothesis is less than. The second term is the degrees of freedom, and then the third term is always 1 because that indicates we're using the cumulative distribution function, the CDF. Again, we don't have to times this by 2 because this is a one-tailed test. We only had to times it by 2 in the last problem because it was a two-tailed test that we specified. We specified not equals. Here, it's less than, so it's only a one-tailed test, and we are looking at that lower tail, so that's why we don't have to times this by 2. So our conclusion then, because our p-value is less than our significance level, we can reject the null hypothesis. We have enough evidence, our sample shows that the true average is likely to be less than 60 seconds. So based on this sample, we can say that we think that the maze does not reach the difficulty level. We have strong evidence to say that the true average or the true difficulty level is less than 60 seconds. So it doesn't meet the requirements that the researcher needs. Now that is how you go about calculating a one-sample t-test for the mean and obtaining a p-value. Now the important here distinction that I want to make is that in this, we do not know, in these problems, we do not know the population standard deviation. That is unknown. In your book, they write this as sigma is unknown. If sigma is known, you can simply just run a z-test. Now, the z-test is easier, but it's less commonly used in application because most of the time we don't know what that true population standard deviation is. So this t-test is really what's more commonly used in applications. In the next set of videos, I'm going to go over the confidence interval for the mean when the sigma is unknown, that is, when the standard deviation of the population is unknown. We can construct an interval much like we did with the proportion tests and still run a hypothesis test. again, just like we did for the proportion test. So the construction is going to seem very similar, but again, we're dealing with an average rather than a proportion, and that's the difference that we want to make note of.